thank you guys so much for coming today. I'm going to be presenting my dissertation research on the accumulation features of persistent organic pollutants in Neotropical Migratory Songbirds. Turn it on. There we go. This is plugged in. I'm not really sure why it's not working. Yeah, almost true. Okay. Is it going to make sense? So just a little, just a little outline. So I'm going to be going some general background information on ecotoxicology. And my dissertation is essentially broken up into three different parts that kind of ask three broad questions. So part one looks at, do migratory songbirds accumulate contaminants while on their wintering grounds? Part two looks at what ecological factors best explain the contaminant levels that I found in these birds. And part three looks at what is the current state of persistent organic pollution research for birds in Latin America. We'll do an overall summary and conclusions and recommendations for future research. Okay, so many North American migratory bird populations have seen significant declines over the past 40 decades. So what we're looking at here is a chart of percent change over time for several subspecies or several subgroups of birds. So for Neotropical migratory songbirds, many of them are aerial insectivores or grassland birds. You can see that some of them have declined up to about 80% of their population. So there are several different threats to population declines in neotropical migrants. So climate change is one of them, habitat loss or modifications, urbanization, predation, and contaminants. However, the impact of environmental contaminants to these population declines is poorly understood. So the class of contaminants that I focused on were persistent organic pollutants, or POPs for short. And they're cause for concern because, one, as their name suggests, they're highly resistant to environmental degradation, so they tend to stay around in the environment for many years after their initial application. The other thing is that many of them exhibit long-range transport, so they can become volatilized and transported in the atmosphere to regions far removed from any type of industrial processes or human activity. They've been discovered in areas as far in like both polar regions, so scientists were actually really surprised when they found them at such high levels there because they were far removed from their initial release. They've been detected in all sorts of environmental media, including air, water, humans, and wildlife. Many of these contaminants are also highly lipophilic, meaning that they like to dissolve in the fatty tissues of organisms. And through this process, they can bioaccumulate within an organism, and they can also be transferred through the food web. Many of these contaminants are also suspected or known endocrine disruptors. So what they'll actually do is they'll mimic natural hormones within the body and can actually cause sublethal effects to an organism. So they can impair reproduction, behavior, natural stress responses, and immune function. Okay, so these pollutants can kind of be broken down into either legacy contaminants or emergent contaminants. So legacy contaminants are considered legacy because we've actually banned these contaminants since the 1970s. So for many decades, however, we're still detecting them in the environment. So I looked at a suite of organochlorine pesticides. So they're any kind of organic compound with chlorine attached to them. They were used extensively in lots of agricultural practices, as well as for vector control for malaria and also typhus. They're actually still used in some parts of the globe, such as Asia. I also looked at polychlorinated biphenyls, or PCBs. This is a type of industrial pollutant, so it's found in all sorts of electrical equipment, paints, plastics, building materials. You can even find them in old light fixtures. I'm pretty sure Naval Hall probably has them. Wouldn't be surprised. Yeah, these were also banned in the 70s, and so you can also see inorganic structure of chlorine atoms that can be attached to any of these locations. So they're considered legacy, like I said, because they've been banned, and we've seen decreasing levels of them in the environment and in wildlife since their banning. However, emergent pollutants, such as brominated flame retardants. So I looked at polybrominated diphenyl ethers. These are another type of industrial pollutant, and these are actually still being currently used, some formulations, and we've actually seen increasing levels of these contaminants in the environment. So they're flame retardants. So basically, they're in any type of material to help reduce the cause of fire or to help slow down fire. So they were introduced to help meet fire regulations. So you find them in a lot of building materials. They're in almost all electronics. They're in your receipts from the grocery store. They're in your couches, upholstery, your car cover seats. So they're pretty much everywhere. Okay, so just a little history of ecotoxicology. So in the 1930s and 1940s was where we first started to have aerial application of many of these organochlorine pesticides. This is also when the insecticidal properties of DDT were first discovered. So DDT was actually first formulated in the 1800s, but we didn't realize until the 1930s that it was a very good insecticide. So you see the increase in the use of these organochlorine pesticides. In the 1950s, we continued to synthesize additional pesticides and continue to increase the use of these contaminants. And it's actually in the 1950s where we first started to see the very first studies of contaminant accumulation in wildlife. So just to kind of show you how prevalent and how widely used these pesticides were used, I found this old archival footage from city officials in San Antonio using this stuff.
With the possibility of a grave infantile paralysis epidemic, San Antonio health authorities attacked germ carriers on a citywide front. With more discovered DDT and special sprayers, sections of the city are literally fogged with the insecticide in the fight to stop the spread of polio. Every suspected spot is sprayed. The drastic cleanup is ordered as polio and allied diseases show alarming increase. Even sprayers come in for disinfecting. And in the parks, precautions are taken to prevent gatherings of youngsters. Literally tons of DDT are used on this dread disease that attacks our young. Again, war, destructive and terrible, contributes one of its discoveries to save life.
So you can see, like, literally tons of this stuff were sprayed on everything, everyone, and everywhere. So used quite a bit. Okay, so DDT is the parent compound of the pesticide, and it's kind of the poster child of contaminants. So here on the left, we have the parent compound of the chemistry, but essentially in the environment, DDT is degraded to its primary metabolite called DDE. So this is what we find most often in the environment. And this process actually takes quite a long time. It can take anywhere from 2 to 15 years. So this is primarily, because once again this has been banned, primarily the metabolite as DDT that we find in wildlife and the environment. Okay, so it's actually DDE, the metabolite of DDE, that was responsible for significant population decline of many large species of raptors and aquatic fish-eating birds. So DDE actually accumulated to very high levels in these birds and interfered with their reproduction by causing eggshell thinning. So here on this figure here, you can see some very thin eggs. So what would happen is that when these birds would lay their eggs, they would interfere with the calcium deposit for these eggs. And the shells were so thin that the eggs would become crushed as the birds were trying to incubate them. So this resulted in very high mortalities. So it reduced clutch sizes and it reduced hatching success, and it pretty much decimated these populations. In 1963, there were only 417 nesting pairs of bald eagles. So some effects of persistent organic pollutants in songbirds that we have observed. It can actually alter songs in black-capped chickadees. It has been shown to impair orientation for migration in European starlings. So starlings that had high levels of PCBs weren't able to properly orient in a southward direction during migration. It has also been shown to affect the nest building behavior in tree swallows. So tree swallows that had high levels of these contaminants had reduced nest quality size, so the nests weren't built as well, and they also had fewer feathers. So all of these sublethal impacts can affect the population level. And so although many of these contaminants are considered legacy contaminants, they're still actually a current problem. So these are just a few news article clippings or papers that I've collected since I've been here. Probably one of the most alarming things was recently American robins were actually dying from high exposure levels of DDT at a Superfund site in Michigan. So most of these contaminants cause sublethal effects, so that means that they're not toxic, like highly toxic, or cause a lot of mortality. So these were at really high levels that they found in the brain to cause us to die. Recently in Montana, there was an instance where a roost of big brown bats were actually intentionally poisoned with DDT in a government building. So somebody got a hold of this like decades-banned contaminant and poisoned these bats. California condors, which are still threatened, and they actually still suffer from eggshell thinning from DDT hotspots off of the Gulf of California, are still suffering from these legacy contaminants. So even though they've been banned, they're still a current issue. Okay, so one of the first things that we need to ask ourselves in order to determine how these pollutants are potentially impacting populations is to determine where and when migratory birds are at most risk of exposure for these contaminants. So that's what I try to answer in part one of my dissertation. So nearly 3/4 of North American birds migrate, huge percentage. So of those 3/4, wood warblers comprise the largest group of neotropical migratory birds. So these are all birds in the Parulidae family. They're small perching birds that sing very pretty songs. And these are also mainly insectivorous birds. So neotropical migrants are considered long-distance migrants. So they breed across North America, all the way from the United States to Canada and Alaska. And in the fall, they'll migrate to their wintering grounds in Latin America, so as far south as Mexico, Central America, and down into South America. So this is just a GIF from the Cornell Lab of Ornithology. And so each of these individual dots that you see here are individual species of birds, not necessarily songbirds, just migratory species in general. And this is throughout the annual cycle. So you can see that these birds cross vast geographic areas. So one, they're important because they link these ecosystems together. But in addition, due to these annual movements, these birds can be exposed to a wide range of environmental contaminants over large areas. Okay, so what impact can migration have on contaminant accumulation? So previous studies have already shown that there are seasonal differences in contaminant body burdens in migratory songbirds. So in the 1960s, a researcher by Henny et al. Actually looked at migrating peregrine falcons, and what he found was that when birds were returning in the spring from their Latin American wintering grounds, they had elevated levels of organochlorine pesticides in their blood. So what he figured was that they were being exposed to these contaminants on their wintering grounds. And this has been observed for other species of birds in different parts of the globe. So a very common hypothesis for a long time has been that migratory songbirds are accumulating these pesticide contaminants while they're wintering in Latin America. So my main objective for this first chapter was to determine seasonal variation of contaminant accumulation in migratory and resident songbirds. So my target species, so all the migrants that I looked at were species of warblers. So again, these are small insectivorous perching birds. And in addition, I also collected resident species of birds. So resident birds tend to stay in the same area year-round. They have very small home ranges. So they're really good indicators of local background contamination because they don't move. So we also collected songbird species that were also insectivorous, and they were basically our reference group. So they would let us know what the levels of contamination were in a local area. Okay, so I have 3 main study sites. So we have 3 study sites in Texas. We have 2 study sites in the Yucatan Peninsula of Mexico. So this is a very common stop very popular stopover site for many migrating birds across the Gulf of Mexico. And then we also had two sites in Costa Rica. So we captured birds in the fall in Texas as they were moving from their breeding grounds south to their wintering grounds in Mexico and in Costa Rica. So we collected both migrants and residents while they were on their wintering grounds. In addition, we collected songbirds in Texas again in the spring as they were returning from their wintering grounds. So we got that full cycle of migration. Okay, so birds were collected using 12 and 6-meter mist nets at each of the locations. So birds, once detected in the net, we removed them. They were euthanized using thoracic compression, and in total we caught 153 birds. If you guys want to hear an awesome story at the end of this about how I met Will Smith in Costa Rica while I was collecting, ask me about it then. So yeah. So methods for lab analysis. So once I had the birds, I actually removed all the feathers, removed the head, removed the tail, and removed the wings. And I homogenized the carcasses. We freeze-dried them, and they were solvent extracted using an accelerated solvent extractor. And through a series of columns to clean them up, we concentrated them down in order to put them in a GC mass spec analyzer to determine which types of contaminants were present and at what level. So what did we actually find? Okay, so I'm going to start by talking about the contaminant profiles. So what we have here is we have the 3 major contaminants that I found, which were PCBs in yellow, DDE, which again is our metabolite of DDT, the pesticide, and PBDEs, which is our flame retardant. And this is based on the location and the season. The M stands for migrant and the R stands for resident. So you can see within a location and between migrants and residents that there's quite a bit of variability. However, in general, we can see that both PCBs and DDE comprise about 80% of the total contaminant body load. So this is if we were looking at all the contaminants together, which ones contributed the most load. And that was PCBs and DDE for both migrants and residents at each of our locations. PBDEs, on the other hand, usually contributed a lot less, usually about 16% or less for these groups. Okay, so now I'm going to talk about the contaminant profiles of the PCBs. So this is the general structure of the PCBs, so biphenyl ring. And so each of these positions can be substituted by a chlorine atom. And so the position and the level of chlorination, so how many chlorine atoms are attached to these tells us the source of the mixture, and it also determines the fate in the environment and also how they can accumulate in birds. So we often look at these to determine the toxicity. It can also determine the toxicity. So we usually group them based on the number of chlorine atoms they have, and they're called homologs. So what I'm going to be showing you is the homolog profile. So what we have here, so then you actually sum all of those individual congeners to get a total. So what we have here is the percent contribution to the total PCB contaminant load based on the level of chlorination. So di stands for 2, tri for 3, tetra for 4, etc. So migrants are on the left and residents are on the right. So what we can see here is very clearly that the patterns between migrants and residents are very similar. They tend to be contaminated mostly with the penta, hexa, and hepta, so 5, 6, and 7 level of chlorination levels. So what this tells us is that there are likely sources, the likely sources of PCBs are the same for both migrants and residents, and the retention and metabolism of these pesticides is similar between the 2 species. So you can see like there are obviously individual variations between sites, but in general, they're very similar. And so we actually see this in other species of birds, such as aquatic birds, in other regions. So now looking at the percent contribution of PBDEs, so this is again is our flame retardant, but instead of looking at homologs, we're actually looking at individual congeners of PBDEs here. So migrants are at the top and residents are down here at the bottom. And again, the y-axis is the percent contribution, and on the x-axis we have the individual congeners. And so what I found was that basically 5 individual congeners contributed about 90% of the total contaminant load to these birds. And they were very similar for both migrants and residents. So this is very indicative of a DECA PBDE mixture. water. So similar sources. Again, you can see individual variation between sites, but in general, very similar for both migrants and residents. Okay, so now I'm going to talk about the actual levels, individual levels that we found. So this is the geometric mean of DDE. So we have the concentration of DDE in nanograms per gram dry weight on the y-axis. And on the x-axis, we have the location and season. So we have Texas in the fall, Yucatan and Costa Rica in the winter, and then Texas in the spring. So looking first at migrants, you can see that there's kind of no general pattern that we see of exposure between fall and spring or the wintering locations. The only significant differences that I found were between migrants returning in the spring in Texas compared to migrants that I collected in Costa Rica. The birds from Costa Rica were significantly less contaminated compared to those in the spring. However, when we look at resident species, this tells a very different story. We can see that both resident species in Yucatan and Costa Rica were significantly less contaminated than resident species we collected in Texas. You can see that there's, for Texas in the fall, very high ranges for DDE. So this is likely due to, in Texas in the fall is when I had the 3 sampling locations in Texas. So one of them was in near College Station, so very close to an urban environment. However, I didn't have that location in the spring. So I think that accounts for this large variation that we see here in the fall. So what this tells us is that there's very low exposure of DDE while migrants are on their wintering runs because we don't see those high levels in the resident species. When we compare migrants to residents, the only significant differences that I found were between migrant and resident species from Costa Rica, where migrants had elevated levels of DDE compared to resident species. Okay, now looking at PCBs, so again, our industrial contaminants. So looking at migrants, you can see there's no clear pattern of accumulation, essentially levels. There were no significant differences between migrants at any of the locations or between fall and spring. However, when we look at the resident species, again, resident species from Costa Rica have significantly lower levels of PCBs compared to resident species in Texas and Yucatan. So this intuitively makes sense because, again, this is an industrial contaminant, so you wouldn't expect to find it in remote regions. So our sites in Texas were located in more industrial areas as well as Yucatan. When we compare migrants to residents, again, it was only birds from Costa Rica that had significant differences, where migrants were more contaminated compared to residents. Again, what we would expect. So looking at PBDEs, for migrants, we didn't see any significant differences between any of the locations. So in general, levels were pretty the same. Birds from Yucatan and Costa Rica had slightly lower levels, but they were not significant. However, when we look at resident species, residents from Texas, again, were more contaminated than those that we found in Costa Rica and Yucatan. For both. So again, this makes sense because this is an industrial contaminant. We wouldn't expect them to find higher levels in more remote regions. When we compared migrants to residents, we didn't see any significant differences between the two groups. But what was interesting was that resident species from Costa Rica actually had levels, individual ranges that exceeded those that we collected for migrants. This could, however, be due to small sample sizes. Okay, so are these levels of contaminants actually harmful to these birds? So for DDE, the kind of benchmark level is about 4,000 nanograms per gram wet weight are usually associated with those reproductive impairments that I talked about earlier. However, these values are used for aquatic and rectorial birds. For PCBs, Ney et al. Looked at house wrens, and he found that about 6,000 nanograms per gram wet weight is when he started to see reduced hatching success of nestlings or impairment in nestlings. So levels that I found in my birds were well below these concentrations. For PBDs, Ang et al. Measured European starling eggs, and he found that at approximately 10 nanograms per gram of weight, he didn't see any type of reproductive problems. So our values were similar within this range. Henny et al. Observed in ospreys that anything above 1,000 nanograms per gram of weight, he started to observe problems with reproductive impairment. So again, in general, most of our levels were well below this. However, I did have one Carolina wren from Texas that actually exceeded these values. So these are very high values in general and also high values for a small songbird. But in general, our levels were in the hundreds, so well below these ranges. Okay, so overall summary and conclusion. So I found relatively low but detectable levels of all of these contaminants with all birds at each of the locations. However, most of these levels were below those values known to cause any type of adverse health effects. And I found no significant accumulation of pesticides or other contaminants in migratory songbirds while they were on their wintering grounds. It was actually resident birds in the wintering grounds that had the lowest levels of these contaminants. So that tells us very low exposure and acquisition of contaminants and migrants in these areas. Birds that breed in more northern latitudes are more contaminated with industrial pollutants. However, those wide ranges of PBEs in the residents warrant future research. And these are also the actually first reported levels of PBEs in passerines for all of Latin America. So in general, good news. So besides migration, there are other several factors that can impact contaminant accumulation. So physiology can have an impact. So, for example, differences between males and females. Your habitat can impact contaminant accumulation. Your diet actually has a huge impact on contaminant accumulation. So most terrestrial organisms are exposed to contaminants through their diet. So for the second part of my dissertation, I wanted to look at what ecological factors best explain contaminant levels in birds. So as I mentioned early in my presentation, that many of these contaminants are highly lipophilic, so they're hydrophobic. So it means they don't like to be in water, so they adhere to sediment or organic matter, and also in the fatty tissues of organisms. So here we have an aquatic food chain. So organisms that are low on the aquatic food chain will accumulate a little bit of contaminants, so they'll bioaccumulate, but then these contaminants can biomagnify through the food web. So the higher you are on the trophic scale, the more contaminated you are because you're accumulating all those lower level contaminants that have been stored in the fat from each level below. And so it's at these levels that you start to see those adverse health effects. So in general, the higher you are on the trophic scale, the more contaminated you are. So your diet has been shown to affect contaminant accumulation in songbirds. So this is a study that was done where they measured levels of DDE, here on the y-axis, in several species of grassland passerines based on their diet. So what they found was that birds that fed on on many insects on a higher trophic level were more contaminated with DDE compared to birds at a lower trophic scale that were mainly feeding on seeds. So we see this biomagnification even in these small terrestrial passerines. So stable isotopes are often used to examine diet. So you guys have heard of the expression, you are what you eat. So in stable isotopes, we say you are what you eat plus approximately 3 parts per mil. So 3 parts per million is usually the difference between one trophic level to the next. So nitrogen is used as a proxy to determine your trophic level. So the higher you are on the trophic scale, the more enriched you are with nitrogen. In addition, carbon can tell us the plant-based source. So, So C3 plants generally tend to be more depleted in heavy carbon. So their ranges are usually negative 28 to like negative 22, and then C3 grasses tend to be more enriched, so they'll have less negative values. So they can tell us the plant-based source. So in addition, previous studies have shown latitudinal trends of DDE in birds. In a meta-analysis, Moore et al. Observed that birds breeding in more southern latitudes had elevated levels of DDE compared to those in more northern latitudes. So we can use deuterium to tell us about migration and breeding origins, and basically use it as a proxy for latitudinal differences. So what we have here is a isoscape map of deuterium, so it's an isotope landscape. So each of these individual color bands represents a different level of deuterium. So heavy isotopes due to precipitation patterns. As they move across the continent and more northern regions, heavy isotopes are rained out earlier, and you have these distinct bands occurring. So the more north you get, the more depleted and heavy deuterium you are, so the more negative the values are. So precipitation has distinct isotopic values. So when it rains, that precipitation gets incorporated into plants. Bugs then eat those plants, and then birds eat those bugs. And when they molt new feathers, whatever they're eating, whatever's in their diet is representative of the local background area. So the deuterium values in feathers are highly correlated to precipitation values. So we can determine where these birds are breeding. Okay, so my objectives for this chapter were to examine any differences in diet using stable isotopes of carbon and nitrogen between migrants and residents, and also to determine which factors, i.e. migration, diet, location, or status, so migrants versus residents, best explain the contaminant body burden. So my methods. So for the feather analysis, I took the first and second primary feathers. I cleaned the feathers in a 2:1 chloroform methanol solution. I homogenized them, and then all of those feather samples were analyzed for deuterium to determine breeding origins, and then a subset was analyzed for carbon and nitrogen. I also analyzed liver and stomach contents. So a portion of the liver and all these stomach contents from the crop were removed. These were dried either in the oven for the liver or air dried for the stomach contents. They were homogenized, ground to a powder. A subset of liver was analyzed for nitrogen as well as the stomach contents. And then the remaining liver samples were lipid extracted using a chloroform methanol solution and then analyzed for carbon. Okay, so what did we actually find? So in terms of breeding origin, so this is looking at the deuterium. So what we have here on the y-axis is the deuterium value. So remember, the more northward we go, the more depleted we are, so the more negative the values. And we can see here that our groups from Texas are coming from more southern latitudes, which makes sense. Same with our birds from Yucatan and our birds from Costa Rica. So very, very close ranges. However, when we look at the migrants, we can see that they're basically all over the map. So they're literally coming from all across North America. Okay, so this is looking at the liver and stomach content. So this is looking at the carbon values at individual variation. So this is looking between locations and between migrants and residents. So TX stands for Texas fall migrants, and then we have Texas fall residents, etc. So you can see between migrants and residents and between locations, there's a large amount of variability, individual variability. The same thing is observed for the liver samples. When we look at nitrogen, again, we see a lot of large individual variation between locations and between migrants and residents, and also potentially shifts in the baseline nitrogen value. Same thing for liver, lots of individual variation. So when we look at the means for these, so this is looking at a biplot of nitrogen and carbon. So first looking at Texas, however, even though there's a lot of individual variation, when we look at the means, we can see that the mean values for both carbon and nitrogen are very similar between migrants and residents. So what this tells us is that they're feeding at generally similar trophic levels, because it's less than the 3 parts per mil, and also a very narrow carbon range. However, when we look at birds from Yucatan, we can see that migrants are significantly enriched in nitrogen compared to residents. It's actually by about 3.65 parts per mil, so this means that they're actually feeding at a higher trophic level. Ranges for carbon are larger than those compared to Texas, however, still pretty similar. When we look at birds from Costa Rica, migrants are slightly enriched in nitrogen compared to migrants, however, it's not a difference of 3 parts per mil, so in general, they're still feeding at similar trophic levels. Much larger ranges for carbon. So for carbon, in general, these birds are feeding primarily on a C3 plant basis. So these are your trees and your shrubs, because their values are generally between -20 and -34 parts per mil. However, for some of the Costa Rican birds, you can see that the ranges are much larger, So we have species that are actually also feeding on tropical grasses that are generally more enriched in carbon. But in general, overall, from these figures, these birds have very similar diets. Okay, so this is looking at the correlation between the stable isotopes in liver and stomach contents. So here on the left we have carbon, and on the right we have nitrogen. And on the x-axis we have liver, and y-axis we have stomach contents. So you can see for both migrants and residents, for both carbon and nitrogen, there's a significant positive correlation between the two. So what this tells us is that the diet that the birds were feeding on in the area has already assimilated into their tissues. So we know that the liver tissues are representative of the local diet. However, when we compare stable isotope values in the liver to feather, we see that only resident species for both carbon and nitrogen had a significant positive correlation, whereas migrants did not. So what this tells us is that resident species have a consistent diet throughout the year that doesn't really change. Whereas resident species, this could either be due to shifts in diet or changes in baseline isotope values for both carbon and nitrogen. So liver is indicative of recent diet, whereas feathers are indicative of more long-term diet. Okay, so now we're going to look at the relationship between stable isotopes and contaminant body burdens. So this is looking at DDE versus liver nitrogen. So if you remember, nitrogen is used as a proxy for your trophic level. And in general, the higher you are on the trophic level, the more contaminated you are. And then they were separated by location. So Costa Rica birds are in circles, Texas in triangle, and Yucatan in square. So looking at resident species first, who are in white, I actually found a significant negative correlation between levels of DDE and liver nitrogen. So you can see our birds from Costa Rica are down here, which were the least contaminated. So this is actually opposite of what we would normally think to find. They were slightly more enriched compared to birds from Yucatan, resident species from Yucatan and Costa Rica were slightly more enriched in nitrogen compared to those in Texas. However, we found this negative relationship. So what this likely tells me is that either there are no differences between nitrogen values, or that the insects that residents were feeding on in Costa Rica and Yucatan are less contaminated than insects from Texas. When we look at migrants, however, we found no significant relationship between DDE levels and nitrogen values. So looking at PCBs, for the resident species, no significant relationship was found between contaminant levels and nitrogen values. Same thing for migrants, no significant correlation between the two. Looking at PBDEs, again, no significant relationship between nitrogen values or PBDE levels, and same thing for migrants, no significant relationship. So now we're going to look at feather deuterium, again as a proxy for latitude between each of the contaminants. So for DDE, for resident species, there was a significant positive correlation between these two. So again, DDE is really good at separating out our individual populations. So we have our birds from Costa Rica, Yucatan, and Texas. However, when we look at migrants, there was no relationship found. Again, for PCBs, a significant relationship was found for residents. However, nothing was found for migrants. When we look at PBDEs, again, we found a significant relationship for resident species, and we actually found a significant relationship for migrants. However, it was a negative correlation. So in general, migrant birds that were breeding in or were coming from more northern latitudes had elevated levels of PBDEs compared to those from southern latitudes. However, these relationships were relatively weak. So I put all of these individual variations into a multiple linear regression model to see which ones best explain the contaminant body burdens. So I have, so in the model, I looked at nitrogen, so diet, trophic level by itself, deuterium, so where the birds were coming from, location, where we sampled the birds, the interaction between trophic level and status, so either migrants or residents, deuterium in the interaction with status, and then also location and status, and then the full model that looked at location, status, and interactions with the stable isotopes. And what I found was that, that should actually be moved down, was that for DDE and PCBs, location and status best explain contaminant body burdens in the songbirds. However, for PBDEs, it was the full model, so the interaction with the stable isotopes that best explain contaminant body burdens. So essentially what this is telling us is that diet is a very poor predictor of contaminant levels, and it's actually location and likely historic use that best explains levels that I found in these birds. Okay, so overall summary and conclusions. So stable isotopes revealed really only minor differences in diets between the birds within each of the locations, except for upwards from Yucatan. Diet alone, through the use of stable isotopes of carbon and nitrogen, was a really poor predictor of contaminant body burden. And so this could be due to baseline nitrogen values varying significantly between locations. So it kind of makes it hard to really accurately determine trophic level. Multiple linear regression models show that location and migratory status best explain the contaminant burden. So this suggests that historic use and location is likely the source of contaminant exposure as opposed to diet. So for the last part, I kind of wanted to see how my levels that I found in my birds how they compare to levels for other passerines in Latin America. So despite the fact that 3/4 of North American birds migrate to the Neotropics, most studies have actually focused on temperate regions. So most studies have been conducted either in the United States, Canada, or in Europe. So this is actually by our own Dr. Lockard in '97. Not much has actually changed since then. And this is also similar for review studies. So most reviews tend to focus on North America and Canada and Europe. And there has actually been no systematic reviews for birds conducted in Latin America. So the objectives for this last chapter were, one, to determine where and what data was available for persistent organic pollutants in birds in Latin America. So looking at not only the spatial spread of the data, but also the temporal spread of the data. To determine if levels of POPs are actually decreasing in these birds, as we have observed in North America and Europe, and what are the knowledge gaps and recommendations for future research. Okay, so this is looking at the temporal spread of the data. So in total, I found approximately 60 studies that have been conducted since 1980. So that average is about 5 or 6 studies every 5 years. So really, not a lot has been done. It really hasn't been until about 2011 that we've seen a significant increase in the number of studies that have been coming out of these regions. So within these studies, looking at the most detected types of contaminants, what I found, so these first 3 are all industrial types of contaminants. The rest of these are all the organochlorine pesticides. And this is looking at total DDTs, but primarily DDEs, what I found. So you can see that most of these studies, the most reported and most found contaminant was DDE, followed by PCEs. Very little information was found for PBDEs, and almost nothing was found for dioxins and furans, and variations for these other organochlorine pesticides. So it's also hard because some of these studies didn't always analyze for the same suite of organochlorine pesticides. So data was limited in this respect. So this is a map of Mexico and Central America, and what it's showing you is different levels that have been reported for all the studies conducted on passerines in these areas. So the values, my values compared to these are here. For Costa Rica was about 17 nanograms per gram wet weight, so significantly less than what has been previously reported. And same for Costa Rica. You can see my bar graphs are almost invisible. So much, much, much lower levels than what has been previously reported for these species. Most of these studies were conducted in the 1980s and 1990s. The most recent study was conducted in 2003 by Clemens et al., and his values down here is about 16, which was similar to what we found. But in general, our values were much, much less than what's been previously reported. Okay, so this is looking at the geographic distribution of the studies. So here we have Mexico and Central America, and then we have South America. And individual dots indicate where data exists for these birds, so where these samples were collected. The color scheme is indicative of the number of studies that have come out of those countries. So right away you can see that Mexico and Brazil contribute the most to the studies. So Mexico leads by and large, so approximately 42% of all studies have come out of Mexico, followed by Brazil, which only accounts for about 17%. So even the difference between the first two countries, Mexico doubles the number of studies compared to Brazil. There's virtually no data for Central America, except for Costa Rica and Panama. And for South America, Bolivia and Paraguay also have no data. So in addition to that, you can also see that the locations of where these studies have been conducted have been highly concentrated on coastal regions. So most of these studies have focused on aquatic habitats and also aquatic species. Very limited stuff for interior parts of the country or terrestrial systems. So this also highlights why the current research is so important, because there's so little information on terrestrial species and habitats. So now looking at the temporal trend of analyses. So this is looking at levels of DDE from samples collected from 1960 until present. So this is looking at all of the birds from all of the studies. So we have many different tissues and many different diets. But in general, we found a significant decline of the levels of this contaminant. But again, take it with a grain of salt, because it's looking at many different species with many different diets. However, if we break them down into their different breeding yields, we found a significant decline for fish-eating birds, so piscivorous birds, of DDE. However, if we look at wading birds that feed primarily on aquatic inverts, I actually found a significant increase in the levels of DDE. However, this group of birds was probably the most diverse in terms of species and also in terms of diet. So yes, they're all feeding on aquatic invertebrates, but that can mean many different things. It can mean aquatic insects, or it can mean mollusks, or things like that. So a lot of diversity. So when we look at passerines, I found a significant decline in DDE levels, as well as for large raptors. So good news. So when I looked at PCBs, when I looked at all birds, I found a slightly significant decrease in the levels of contaminants. However, again, this is looking at all types of birds, many different species, many different tissues, and many different feeding yields. Okay, so overall summary and conclusion. So going back to my first main question. So are migratory songbirds accumulating contaminants while on their wintering grounds? I found no significant accumulation of pops in migrant songbirds while they were wintering in Latin America. So it was actually resident species from Texas that generally have the highest levels of persistent organic pollutants. And the levels of contaminants were generally those below those known to cause any types of adverse health effects. So all good news. So looking at what ecological factors best explain contaminant levels. So diets between migrants and residents were generally very similar. So I saw no huge differences in trophic level, except for my birds from Yucatan. And diets were generally very poor predictors of contaminant body burden. It was only resident species that showed significant correlations between contaminant body burdens and deuterium levels. So again, that suggests that location and historic use is primarily the source of contaminant exposure. And that's what we found in our multiple linear regression models. That location and migratory status best explain contaminant burdens. Okay, so in terms of what is the current state of persistent organic pollution research for birds, there are significant data gaps in POPs levels for much of Latin America, and particularly Central America. I saw pronounced geographic bias, so current data is highly concentrated in coastal regions and aquatic ecosystems. Data on PCBs is really limited and very scarce for PBDEs and dioxins and furans. Levels of these persistent organic pollutants are likely declining. However, the limited data, due to the limited data and the confounding ecological variables, makes these interpretations kind of hard. But most likely they're declining, as we've seen in North American and European birds. Okay, so recommendations for future research. So future studies should also include PBDE, dioxins, and furans in their analyses. In addition, there are newer classes of pesticides that are being used extensively in Latin America. So the impact of these pesticides on these populations is also very limited. Studies should also focus on terrestrial habitats and species. Also strongly links towards populational level effects. So a lot of the studies that I looked at had quoted benchmark level effects, but not many of them actually tried to examine links to populational level effects. So looking at hatching success or nestling success, it was generally like, these are the levels we found in the birds. They're above those known to cause adverse effects, or they're below. Analysis of museum specimens may provide a more robust prime trend analysis. So at the beginning of this project, my main question was to determine if migratory songbirds were accumulating contaminants while on their wintering grounds. But at the end of the project, I started to ask myself, well, is it possible that these birds coming from North America are actually a source of pollution to areas of Latin America that actually have lower levels of contaminants? So that can be somebody else's future. So with that, I'd like to thank very many people. This project was really large in terms of geographic scope. So I'd like to thank my advisor, Dr. Miguel Mora, my committee members, Dr. Volker, Dr. Sericiano, and Dr. Grossman for teaching me all about birds, contaminants, and stable isotopes. All of my friends that got up at the butt crack of dawn to help me catch birds in the field. Thank you guys so much. And particularly to Faith Bird, she helped me truck mist net poles up and down the mountains of Costa Rica. Very hard. To the Gulf Coast Bird Observatory, UGA Costa Rica, La Selva Biological Research Station, and our collaborators in Mexico that helped catch some of these birds. A lot of people really didn't want me taking birds and killing them, especially songbirds. So it was really hard to find places to actually do these things. So thank you. Also, I would not be here. Sorry. Due to my many friends. Thank you to my friends and former professors at Carroll College who have supported me. They bought me many drinks and food as a professor. My many friends here at A&M who made this experience so much fun. Thank you guys. Could not have gone to grad school without you guys. To my cat Leo, who spent many a night with me while I was reading or writing, and also thank you to my family, who I owe a lot to. So with that, I'd like to take any questions.
Any questions from the audience?
Yes.
So how long does that contaminant last in the body of birds?
Oh, yeah, so that's the other issue, too, is that a lot of these contaminants will stay for a really long time because they're dissolved in the fatty tissues. So sometimes it gets them metabolized as like they're moving or burning fat, but they can stay for many, many years. So that's also the hard part is when you're trying to determine sources, these contaminants are coming from all over the area.
So they're simply accumulating.
Yep, yeah, so, and also like the older you are, the more contaminated you are.
So you look at the difference between the birds.
I didn't, but previous studies have. Yes, that is a confounding factor, which makes it hard to determine where they're collecting these contaminants. Yes. Yes.
And along the same lines, do they pass some of their contaminant load onto their offspring?
Yes. So yeah. So for there's significant contaminant transfer because when you're laying eggs, it's a lot of fatty material, right? So yeah, the nestlings will actually are exposed to high levels of contaminants from their mother, and actually you can see like differences in egg laying sequence. So the first egg usually is the most contaminated, followed by the second, third, and you actually see differences between males and females. So in general, males will be more contaminated compared to females because it acts as a degradation process as they lose those contaminants in their egg laying. Yeah, good question. Yes, sir.
I think you said that feathers are indicative of long-term diet.
Yeah, well, longer-term diet.
Can you explain that to me? How can that be?
So it has to do with isotopic turnover rate. So how cells are being turned over in the body. So liver has a very rapid turnover of only 9 days, so that's why it's indicative of recent diet, whereas it takes longer for turnover in feathers.
Are feathers active all year?
No, they're not active. So that's the other, so I guess maybe not longer diets, but older diets. So whenever that bird grew that feather,
Okay.
it's indicative of what they were eating at that time.
That's a much better way of saying it.
Yes, sorry. Older diet.
Yes.
Good clarification point, Dr. Mulker, thank you.
I believe I read that in one of your chapters. So I want to change that word.
Okay, all right.
Any other questions? Well, I guess, thank you, Alejandra. We are going to probably spend some time here to have a little
Yeah,
break.
please eat all the food. There's lots of drinks. My friends made delicious food, homemade from scratch. Please eat it all. And thank you for your time.
We'll have some break and then the committee will.
Right now, I'm really looking at I was looking, when I was looking at her presentation, I was like, oh my gosh, I was like, I missed all of it.
Well, you know that the department.